Hi there. I thought we'd spend some time with particle motion. This is a huge part of the applications of the derivative in calculus AB. Um, I will tell you that I've kind of already written in a lot of the details. And so, just as a way to give you a heads up, you may need to pause to make sure you get all of those details in the formula work, because I'm going to try to go through the examples and spend a little bit more time on those. Something that we need to think about is we're going to talk about particle motion as an object moves in a line. So it's either moving along the x-axis or it's moving along the y-axis. And our focus is going to primarily be on position, velocity, and acceleration. But I don't want you to get worried about that because we've really done all of this work before. We're just calling it by a new name now. So, something to think about as we look forward to them. And I think we need to get a good definition of the velocity here. Now, the average velocity, and you may have done some of this in your physics class, the average velocity is the position, the difference in the positions, that's my top, over the difference in time, or the amount of time that it took you to get there. Now, I'm using P of t as our position equation so that you'll kind of know what I'm talking about. The average velocity, I want you to recognize that you didn't need any calculus to do that to calculate that average velocity. However, if I want the instantaneous velocity, I want the velocity at that moment in time, that's going to require calculus. Now, let's take a look at an example. And again, if you need to pause so that you can get all of those details down, please do. That way you have all of the good explanations. So look at this example. We have a particle's position is given by this function where P of t is the measure in centimeters and t is in seconds. So what is the average velocity on the interval from t equals 1 to 3 and indicate units of measure? So I have my calculator right below this picture here because I want to use it. So I'm going to put in this position equation, E of t times sine of x. And I'm going to go ahead and zoom 6. And what I'm going to be doing, because this one, remember, does not require any calculus, I'm going to use my calculator to just find my values. So I'm going to do P of 3 minus P of 1 over 3 minus 1. Now you may be asking yourself, wait, you flip-flopped A and B. You're right, I did. Does it matter? So if I do P of 3 first, then I need to make sure I put 3 first in the denominator. So let's do second trace, and we're doing value, and I'm going to put in a 3. And the calculator gives me the value of 2.834. Then I'm going to put in the value of 1, second trace, number 1, and I'm putting in a value for 1, and that is 2.287. And then you can go to your home screen by doing second quit. Let's do the subtraction on these. Minus 2.287. Well, I don't think I hit the minus, did I? You probably saw it. I didn't catch it. Let me add a minus in here. There it is. And we get 0.547 divided by 2. So I'm going to go ahead and divide by 2 in my calculator. And I get 0.2734, because remember AP rounds to 3 decimal places. And my position was in centimeters. And my time was in seconds. Okay. Now to do the instantaneous velocity, this is where I'm going to take the derivative. So my instantaneous velocity is the derivative of the position at 1.5. Now, if you've seen any of my videos, you've seen me take the derivative, but I'll show you one more time. Remember, my function, my position is in y1. So I'm going to do second trace, choose option 6, and I'm going to type 1.5. And notice my derivative is 4.787 and same units, okay? Centimeters per second. How you doing so far? Okay. Just relating our position and our velocity. Now, I want you to see the connections, okay? I want you to see that the slope of the secant, you remember we have found this way, looks very similar to the average velocity. And really, we're doing the same thing. We're just, when we apply it to particle motion, we call it the average velocity. When we're looking at instantaneous velocity, that's the derivative. That's the slope of the tangent line. So friends, you have been doing average velocity and instantaneous velocity all along. We just weren't calling it that, but now we are. Okay, so average acceleration, my physics people, you remember taking your velocity, the difference in your velocity over the difference in time. And I need to put a note. This is where v of t is the velocity. And the instantaneous velocity is where you're going to do the first derivative of the velocity or the second derivative of the function. Make sure you catch those. Now, if you need to pause at this point so you can get all of those details in the notes, that would be great. I'm going to keep going and work an example, okay? Notice in our example, we're using the same function, e of t, e to the t times sine of t, and we want the average acceleration. So in order to get this, we're going to have to go find the velocity. So let's take the derivative. It's a product rule. First times the derivative of the second plus the second times the derivative of the first. Now I'm going to set up the average velocity. It's going to be my v of 3 minus v of 1 over 3 minus 1. Okay, now go back in your calculator and let's turn off the position function. Remember, you highlight the equal sign and just press enter. The calculator will store the position function, but it won't graph it or won't do any calculations with it. Now you can go to y2 and type in your velocity equation. Cosine of x plus, I'm going to go ahead and put that e to the x in front, and I've got sine of x. All right, and then let's graph this one. Again, I'm just going to ask the calculator to find values for me on this velocity equation. Now, the only one that the calculator is graphing is the velocity, because remember, I turned the position function off. Second trace. Oh, it wasn't done graphing. Let's try that again. Second trace, number 1, and I'm going to plug in the 3. So it's telling me that the velocity at 3 is 17.050. I'll do the same thing at 1. Second trace, number 1, x equals 1. I get 3.756, and that's divided by 2. Now, just like before, I'm going to go to my home screen and do my subtraction. 17.050 minus 3.756 divide by 2. My average velocity is 6.647. Let's think about the units. The units of my velocity were centimeters per second. That was on top. And then on the bottom, the units of time, second. So really what I have is centimeters per second squared. And my physics people will remember that those are the units for acceleration as well. All right, keep pressing on. So what is the instantaneous acceleration at 1.5? So instantaneous acceleration, you'll remember, is the derivative of the velocity. Remember, I have the graph of the velocity currently graphed in my calculator. There it is. So I'm going to ask the calculator to find the derivative. Second, trace option number 6 and type in your 1.5. And we're told that this is 4.787. Units are the same for acceleration, so it's centimeters per second squared. Okay, so far so good. You've got the difference. You've got a couple of examples, difference between average velocity, instantaneous velocity, average acceleration, instantaneous acceleration. So let's make some connections next. Now for these connections, I want you to see that f of x that we've called before really corresponds to the position. And f prime of x, it's going to correspond to the velocity that we discuss. And f double prime, that's going to be our acceleration. So when we make these connections here, when I talk about the velocity being 0, you'll have to relate that to the derivative. And when the velocity is 0, what does that mean on my position? That it has a potential turn around point. Meaning the object could be moving in one direction, and at that second it stops, the velocity is 0, it turns around and moves the other direction. So if the velocity is positive, the position is increasing. Friends, this should sound very familiar to you because we've talked about curve sketching again and again and again. If the derivative is negative, then the position is decreasing. If the derivative changes from a positive to a negative, the function changes from increasing to decreasing. Before, we would have said there was a maximum there, right? It's a little different when your object's moving in a line. And if the derivative changes from a negative to a positive, the function changes from decreasing to increasing. Okay, let's make some connections with the second derivative, the acceleration, and the velocity. So if the acceleration is 0 or undefined, there is a potential change in velocity. Okay. If the acceleration is positive, the velocity is increasing. If the acceleration is negative, the velocity is decreasing. If the acceleration changes from a positive to a negative, then the velocity changes from increasing to decreasing. And if acceleration changes from a negative to a positive, then velocity changes from decreasing to increasing. Okay, all those same connections we had with curve sketching are going to apply with our particle motion. We may call them something different, but we are going to be processing it the same way, analyzing the same way. So I hope that starts to kind of get us thinking about particle motion. We'll continue on this path to make sure that you have everything you need for this portion of the AP exam. As always, if you have questions or comments, please leave them in the comments below. I would love the opportunity to answer those. And don't forget to like and subscribe. That way, you get a notification every time a new video is posted. Bye for now.